In the previous tutorial, we estimated the equations of Klein Model 1. Here, we will use those equations and their results to illustrate the test of endogeneity. In Klein Model 1, we estimated the three equations of consumption, investment, and private wages. As an example, let us consider the investment equation. Here, the variable corporate profits was taken as endogenous, whereas lag of corporate profits and lag of capital were taken as predetermined variables. Using the test of endogeneity, we can check if the variable of corporate profits is truly endogenous or not. This is essential because if it is not endogenous and not related to the error term mu2, then we are better off applying OLS. We should use a simultaneous equation approach only if this variable is truly endogenous. To apply the test of endogeneity, we have to first estimate the reduced form equation of the endogenous variable. This is the same as the first stage of 2SLS and 3SLS models. The reduced form equation of corporate profits will look like the equation shown here. Corporate profit is the dependent variable, which is a function of all the exogenous and predetermined variables in Klein Model 1. Using this reduced form equation, we can obtain the predicted values of corporate profits or pi cap and the estimated residuals of the reduced form equation V1 cap. The predicted variable pi cap is used as the instrumental variable in the second stage. The estimated residuals V1 cap capture the part that is related to the error term of the investment equation, causing bias and endogeneity. When applying 2SLS or 3SLS, we care about the predicted values pi cap. However, in the test of endogeneity, we are interested in this estimated residual V1 cap. Next, we include the error term V1 cap as an independent variable in the investment equation. When we estimate this equation, the coefficient associated with V1 cap, that is, theta1, tells us about the endogeneity of corporate profits. If V1 cap and its coefficient theta1 are significant, then the variable corporate profits is truly endogenous. On the other hand, if this coefficient is insignificant, then theta1 is not significantly different from 0. In that case, corporate profits variable is not endogenous. Therefore, the null hypothesis of this test states that theta1 is equal to 0 and corporate profits is exogenous. The alternate hypothesis states that theta1 is not 0 and corporate profits is endogenous. This is the regression-based test of endogeneity and is equivalent to the Wu-Hausmann statistic. If we apply the f-test that the coefficient of theta1 is 0, then we obtain the Wu-Hausmann statistic and its p-value. There are several other forms and variations of this test that are applied in different situations. Some of these tests can have different null and alternate hypotheses, so it is important to check which version and hypothesis are being applied in the software you are using. To apply the test of endogeneity, we have to estimate the 2SLS model first. Even when we are applying the 3SLS model, the first two stages of the 3SLS are the same as the 2SLS model. So, we can use the results of 2SLS to determine endogeneity even if we are applying 3SLS in the end. In R, we can apply 2SLS using the ivreg function in the AER package. Then, we can use the summary function on those 2SLS results to apply the test of endogeneity. In the command shown here, TSLSINV contains the results of 2SLS. The option diagnostics is equal to true will automatically apply the test of endogeneity and report its results. In Stata, we can use the stat endogenous command to apply the test of endogeneity after estimating the 2SLS model. Even if we are applying 3SLS, we can use this procedure because its first two stages are the same as the 2SLS model. The results of the test are shown in the following table. In R, the Wu-Hausmann statistic is reported along with the p-value. In Stata, both Wu-Hausmann and Durbin statistics are reported. In the results shown here, we can conclude that the variable of corporate profits is truly endogenous and related to the error term of the investment equation. This is because the p-value is less than 0.05 and we can reject the null hypothesis of exogeneity. Hence, we can apply the 2SLS or 3SLS model because the OLS estimates will be biased and inconsistent. The Sargan test can be applied to over-identified models. A simultaneous equation model will be over-identified if the number of excluded exogenous variables is greater than the endogenous variables in the equation. The purpose of this test is to ensure that the instruments used in the first stage of the 2SLS and 3SLS models are not related to the error term. To apply the Sargan test of over-identifying restrictions, we have to first estimate the 2SLS model. Similar to the test of endogeneity, we can follow this procedure even if we are estimating a 3SLS model in the end. After estimating the investment equation with 2SLS, we have to obtain the residuals or error terms of the equation. The error term mu2 cap are estimated residuals of the investment equation. Next, we regress this error term mu2 cap on all the exogenous and predetermined variables of Klein Model 1 which were used as instruments in the first stage. The purpose of this is to make sure that the exogenous variables are not related to this error term. We can calculate the statistic as n multiplied by the r-square of this regression, which follows a chi-square distribution. The degree of freedom for this chi-square test will be equal to the number of extra instruments in the first stage. In our example of investment equation, we have 7 instruments which are exogenous and predetermined variables. 2 of these instruments are present in the investment equation itself, that is, lag of capital and lag of corporate profits. Therefore, we have 5 excluded exogenous variables and 1 endogenous variable. This leaves us with 5 minus 1, that is, for extra instruments and 4 degrees of freedom. The null hypothesis of the test states that the instruments used in the first stage are valid. On the other hand, the alternate hypothesis states that the instruments are invalid. The Sargan test, in fact, acts as a test of the validity of instruments as well as the specification of the equation. If the statistic is significant and we reject the null hypothesis, it either means that we have an invalid instrument that is related to the error term or the equation is misspecified by wrongly excluding an instrument that belongs within the investment equation itself. In R, the Sargan test can be applied with the same command as the test of endogeneity. The summary function on the 2SLS results with the option of diagnostics is equal to true will also report the Sargan test results. In Stata, we can apply the stat over id command after estimating the 2SLS model. The results of the Sargan test are shown in the table here. The p-value is 0.7697, which means that we cannot reject the null hypothesis. Therefore, we can conclude that the instruments are valid, not related to the error term and correctly excluded from the investment equation. For reliable results, the instruments used in the first stage of 2SLS and 3SLS models must be relevant. This is essential because we have to use the predicted values of endogenous variable in the second stage. The predicted values will not be a good instrumental variable for the endogenous variable if we have weak instruments. To apply the test of weak instruments, let us continue with the investment equation of Klein Model 1. In the first stage of 2SLS and 3SLS, we estimate the reduced form equation of corporate profits as shown here. The independent variables in this equation are the exogenous and predetermined variables of our model. The lag of capital and the lag of corporate profits are present in the investment equation itself. The remaining 5 variables, which are excluded exogenous variables, must be relevant and significantly affecting corporate profits. Only then, the 2SLS and 3SLS results will be able to deal with the bias. We can apply the F-test to the coefficients of the excluded exogenous variables. In our example of investment function, these will be the coefficients of government expenditure, government wage bill, trend, taxes, and GNP variable. As a general rule of thumb, the F statistic must be at least 10 for us to consider that the instruments are not weak. In R, we can use the same summary command after estimating the 2SLS model. The option of diagnostics is equal to true will automatically report the results of the F-test for weak instruments. In Stata, we can use the stat first stage command after 2SLS to obtain the results of this F-test. Let us take a look at the results of this test applied to the investment equation of Klein Model 1. We can see that the p-value is not less than 0.05, indicating that the excluded exogenous variables are not significantly affecting the endogenous variable of corporate profits. If we take a look at the F statistic, it is 1.934. This statistic is well below the value of 10, and we can conclude that we have a case of weak instruments. This usually means that we need to find other relevant variables that are highly correlated with corporate profits and uncorrelated with the error term and, thus, can be used as instruments for corporate profits. In our example, we also have a small dataset of only 22 observations, which can also be a problem in case of 2SLS and 3SLS models. Getting more observations over a longer period of time might be helpful as well. Thank you for watching, and I hope you like this series of tutorials.